Okay, let's do a couple of refraction problems. Let's say we've got a boundary between two mediums. We'll do a vacuum or air, and we're going to do water. First thing we want to do is draw in a normal line. I'll draw it like right here. Perpendicular to the surface. All right, I guess close enough. How about a light ray? Should we make that a different color? Okay, I really screwed that up. Here we go. And we'll have an angle. This is the angle of incidence. And that angle of incidence is going to be 40 degrees. Now, this is where light travels slower. Light travels fastest in a vacuum. So we know that this light is going to bend towards the normal from our previous lessons that we've learned. This is the refracted angle, and that's what we're going to solve for. We're going to use Snell's law. Snell's law is n equals sine of the incident angle over sine of the refracted angle. Now, there's really something very important about here. This formula was derived for going from fast to slow. So that means we're going from fast to slow. The incident angle is the light ray that comes in. That goes up here. That's the refracted angle, and that'll be down here. You'll see how that can change around later. Let's try some numbers. The index of refraction for water will be given to you, or you determine it in an experiment. We did that on the YouTube video. So 1.33 equals sine of 40 degrees over sine of the refracted angle. And now we have to solve for R. You ought to be doing it right now. So we're going to take sine of 40. We're going to divide by 1.33. And then we're going to take the inverse sine. Okay, we get 28.9 degrees. Is that any good? Well, let's see. It's smaller than the 40. Hey, I think it's working. It works that way. We're going to slow down. So we go, it bends toward the normal. That agrees. Okay, that's problem number one. What happens if we change this up? Here comes problem number two. We have our border, boundary between the two mediums. We're going to put in a normal line. And we're going to make this up here, say glass. Down below, we'll have air. And there's going to be a light ray. And it's going to come in like this. You know what? Here I go again with the colors. Let me change that color. Yeah, it's blue. And that angle is going to be the incident angle. And it's going to be, say, 25 degrees. Which way is that light going to go? We have a little bit to discuss here. This is glass, and the light travels slow in that. Just think about it, how dense that is compared to, say, air. Air is more like a vacuum, and in fact, that's the way we're going to treat it unless otherwise told. It's going to bend away from the normal. So what we want to do now is calculate the refracted angle. But here's where things get interesting. This whole diagram could be sideways, upside down, it doesn't matter. But the way we've set up Snell's law, we have to keep in mind that it's supposed to be the fast going into the slow. Well, remember, I'll write it in again, fast to slow. What do we got here? We're going from slow to fast. So you got to be careful. Even though this says it's the incident angle, and it is the incident angle, in Snell's law, it was designed to go the other way. So we have to make sure we make that adjustment. So glass, 1.5 for the index of refraction, as we saw in our lab on YouTube. And then the sine of the incident angle, which is actually on the fast side. It's R this time. So even though you might see in a book, you're going to see sine I over sine R, you got to make sure you know what you're doing with the numbers. The unknown variable that we're looking for right now is R. That is actually on top. That's the fast angle. And the angle on the bottom is going to be the 25. Look, I know it's tricky. Just keep remembering, fast to slow. Very often, I write Snell's law my own way. N equals sine fast over sine slow, because that has some meaning to it. Anyway, let's go calculate that R. Once again, you should have a calculator and you should be doing this yourself right now. I'm going to take 25 sine, I'm going to multiply by 1.5, and then I'm going to do inverse sine. Hey, I get 39.3. Does that make sense that the light's going to come in here, it's going to refract, it's going to bend away from the normal, and is 39.3 bigger than the 25? Sure is. So I think this worked out just fine. Let's try another one. Okay. Well, my line isn't exactly horizontal, but it will live. Now, I'm going to come in over here just to mess things up a little bit. Oh boy, this is a little different. We're going to come up here and we're going to say that this is air, and down below we have glass. Now, check this out. I'm going to make this angle here 50 degrees, okay? If that's 50 degrees, what do you think the light's going to do? It's going from slow to fast. So of course, you're going to say it's going to not go straight, it's going to bend away from the normal. Well, let's just see what happens when we plug these numbers into Snell's law. N equals sine I over sine R. I'm going to again say fast to slow. The glass we're using is 1.5 unless otherwise told. Now, is this the fast side or the slow side? Well, compared to air, that's the slow side. So we're actually looking for an angle on the fast side. That's what's up on top. The formula was derived, I say it a million times, going from fast to slow. So the I is supposed to be up here for that derivation. Sine, well, it's actually the refracted angle in our diagram, over sine of the 50 degrees. So we need to try to solve for the angle up on the fast side. I'm going to take the sine of 50. I'm going to multiply by 1.5. And now I'm going to try to take the inverse sine. I get an error. Uh-oh. What went wrong? Well, here's the deal. The light waves, which look like this, are coming out into the fast medium. And they're going to start to go faster, and they're going to move around like this. By the time this light gets to here, this thing has gone so fast, it's going to swing around, and it can't go any further than this. The biggest angle it could possibly go is 90 degrees. It's not going to do that. It's actually going to reflect back in. This is called total internal reflection. How do you know when you have that? Well, for one, if you get an error in your calculator, then you know you've gone too far. See, if you take the sine of 50 and multiply it by 1.5, you're going to get a number bigger than 1. The sine of anything can't be bigger than 1. Now, physically, what's that mean? Instead of the light breaking out and going so fast, it's just going to swing around. It's going to end up reflecting back in. So that's what's actually going on. I demonstrated that on YouTube as well. So let's just see. What is the biggest angle you could possibly have out on the fast side? I think you'd have to agree it's 90 degrees. So I'm going to go do Snell's law again. And I'm going to take that 1.5 and I'm going to do it backwards. I'm going to say sine on the fast side is 90 degrees. And I'm going to go find out what the angle is on the slow side. What is, sometimes I write S for slow, F for fast. What is that slow angle? Well, the sine in 90 is 1. Let's go calculate what S is. We're going to take 1, divide by 1.5, and do inverse sine. I get 41.8. That means if this angle is bigger than the 41.8, you're not getting out. You're going to reflect. For glass, this angle is a special angle. It's called the critical angle. You can calculate it by saying n equals 1 over sine, and they call that the theta critical. So they write a theta. I'll put a 0 there with a subscript of c. The critical angle is a very special angle. If you're trying to get out of a slow medium, if you're beyond the critical angle, you'll have total internal reflection. If you're less than that, you'll get out at some other angle here. So that actually has some very interesting applications. Here's one of them. You might recall some time ago, I had a colonoscopy. That requires a fiber optic probe. They use this sort of thing in arthroscopic surgery. Some of you guys probably got sports injuries. They make a small incision, say, in your knee, and they slip these little hairs of flexible glass rods. That is not a tube, it's solid glass. If you shine some light in here, that's head on. It's going to go straight through. And as long as this thing's not kinked too tight, you're going to be beyond the critical angle. And then you're going to get total internal reflection. So that angle becomes equal to this angle. Here's another normal line. You're beyond the critical angle. You're going to reflect, and you're going to come right out here. And then that light can shine inside your knee or in my intestines. It can come right back out and go back through. The light goes both ways. Waves can travel through each other. Sometimes they can put a second one alongside, and they can go back and forth and have an eyepiece here for the doctor to look through. And this is steerable in there. So that's a pretty good example of what's going on with medical applications for physics, as you know I love to talk about. Okay, so what you want to do is go watch some YouTube videos, look at my refraction lab handout, and then do the lab problem handout. Lots more coming. All right, talk to you guys soon.